Hello, everyone, and welcome to Caltech's 2023 3-Minute Thesis Competition. My name is Kara Watley, and I'm the University Librarian. Caltech Library is delighted to partner with the Graduate Studies Office, Public Programming, and Theater Arts at Caltech for this event. Before we begin our program this evening, I'd like to acknowledge and offer our respect to the past and present Gabrielino Tongva people and their unceded ancestral lands, including the LA Basin, upon which Caltech sits today. We invite you to honor the Gabrielino Tongva with us and acknowledge the Native, First Nations, and Indigenous peoples who have stewarded the lands for which you and your hometown may occupy. Now let's talk a little bit about 3-Minute Thesis. It was originally conceived by the University of Queensland. It's a competition that challenges, for us, Caltech graduate students to explain their research in an engaging and clear 3-minute talk that's intended for a non-specialist audience. The Spring 2023 Issues in Science and Technology, which I came across earlier this week, includes a perspectives article by Marcia McNutt, the president of the National Academy of Sciences, and Michael M. Crow, the president of Arizona State University. The article, titled Enhancing Trust in Science and Democracy in an Age of Misinformation, is worth a few minutes of your reading time, in my opinion. In it, McNutt and Crow state, it is on scientists to articulate the moral and public values of the knowledge that they produce in ways that can be understood by citizens and decision makers. Given Caltech's prominence in science and engineering communities, we feel it's important to give Caltech graduate students the opportunity to practice, communicate their science in ways that resonate and inspire. This year, we received more than 30 submissions for 3-Minute Thesis, and we chose 13 finalists to present their research today. Thank you very much to our preliminary judges, George Porter and Kathy Johnson from the library, and Kara Steemans and Mary Herrera from Public Programming for all of their work. It was very difficult to narrow it down to our finalists tonight. This evening, our 13 finalists will be competing for 4 prizes. Prizes made possible by the generous support of our sponsors for this evening's event. And it's their logos that's on the slide behind me right now. EBSCO, Elsevier, SPIE, IOP Publishing, Science of Synthesis Team of Chemistry, Wiley, and Taylor and Francis. Through their generosity, our finalists will be vying for a $3,000 first prize, a $2,000 second prize, a $1,000 third prize, and a $500 People's Choice Award. Representatives from each of these companies are attending via live stream this evening, and I would like to ask you to join me in thanking them for their support of Caltech graduate students in science communication. It is now my great pleasure to introduce you to our Master of Ceremonies for this evening's event, Brian Brophy. Brian is a veteran actor in the film, TV, and theater industry, and he's director of the Caltech Theater. Brian is also a Fulbright Scholar in India, a George Soros Award winner in Bosnia, and the story coach at Jet Propulsion Laboratory. Brian?
Thanks, Kara. I would now like to introduce our judges who will select the first, second, and third place winners. You, the audience, will vote for the People's Choice Award. Our judges are Professor George Drogowski, a professor of astronomy and data science, as well as the director of the Center for Data-Driven Discovery. Wow, George, you really create such a buzz. After getting his PhD at Berkeley, he was a Harvard Junior Fellow before arriving in Caltech in 1987. He has worked on a number of subjects in astronomy and cosmology, including globular clusters and elliptical galaxies, very distant galaxies, gravitational lenses, binary quasars, the cosmic gamma ray bursts, dark energy, etc. He led 3 large digital sky surveys and was one of the founders of the Virtual Observatory Framework and the rapidly developing discipline of astroinformatics. He is interested in data science methodology transfer to other fields, and in particular, to medicine. Dean Daryl Peterson is the Associate Dean of Graduate Studies here at Caltech. He received a BA in Communication and an MED in Counseling Psychology, both from James Madison University in Harrisonburg, Virginia, and a PhD in Educational Leadership from the Iowa University of Science and Technology in Ames, Iowa. Daryl has over 25 years of experience in higher education and student affairs and has worked with both undergraduate and graduate students at a variety of institutions from coast to coast. Here at Caltech, Dean Peterson coordinates new student orientation, provides support for graduate students in crisis, and serves as a member of the CARE team. Thanks, Daryl. Michelle Judd is the executive director of the Keck Institute for Space Studies, a joint think tank of Caltech and the Jet Propulsion Laboratory that focuses on new space exploration concepts and missions. She earned her undergraduate degree in engineering from Stanford and is a licensed professional engineer in the state of California. This 22-year veteran of Caltech and JPL has an asteroid, 185641, named after her in 2009. She won the NASA Software of the Year Award in 2011 and is part of the Aegis team and received the 2021 Caltech Honorary Alumni Member Award for her ongoing mentorship of students and alums. Thanks, Michelle. Kristen Briney is Caltech's Biology and Biological Engineering librarian. She has a PhD in chemistry and a master's in library and information science, both from the University of Wisconsin-Madison. Kristen is the author of the 2 books, Data Management for Researchers and Managing Data for Patron Privacy. She loves talking to researchers about data management and evangelizing the benefits of the international date standard ISO 8601 and visualizing data using yarn and fabric. Thank you. Roni Goldschmidt is a postdoc in the Department of Aerospace Galton at Caltech. She is broadly interested in experimental fluid dynamics, development of measurement techniques, and leveraging machine learning for imperfect empirical data. Her current research project focuses on the development of non-intrusive, data-driven, and physics-based methods that estimate incident wind speeds from visual observations of natural vegetation. These methods provide physical insights on the flow structure interactions. Possible applications for them include aviation safety monitoring and wildland firefighting. Outside of research, Roni likes to run on mountain trails and watch the sunset on the beach. Good. So now you're wondering all of what is the criteria for judging the presentations? Well, number 1, did the speaker clearly convey their thesis and the significance of their results to the audience? So that's number 1. 2, did the presentation provide adequate background to the research question? 3, did the speaker have sufficient stage presence, eye contact, and vocal range, maintain a steady pace, and have a confident stance? 4, did the oration make you want to know more? So we're going to present the speakers right now. Y'all ready? Yeah. Presenter number 1 is Sneha Ayungu, Division HSS Social and Decision Neuroscience Lab, John O'Doherty Lab, presenting using games to probe the mind.
Hi, imagine yourself on a vacation. Are you the kind of person who likes to plan your entire itinerary ahead of time, or are you the kind of person who likes to make it up as you go? I'm sure you've been on lots of vacations with people, and whichever the kind you are, you're definitely annoyed by the other. And frustrating though it may be, it actually helps to have people who think differently. Because in the course of evolution, as circumstances change, it is likely advantageous to have a mixture of strategies where one strategy is bound to succeed and the species survives. And I think our diversity and variance in decision making is what made us thrive as a species. But the mutations that cause these different strategies can also sometimes cause side effects and manifestations of mental illness, such as autism, schizophrenia, ADHD. So in my research, I hope to understand how the brain employs different strategies and how it differs in different individuals, including those with mental illness. And how I do this, I do it using games. Now, games, as you know, are nothing but simulated environments where you can act and strategize to earn rewards and avoid punishments. And we, as the makers of the game, can control everything that happens in the game. And how do I go about my research? First, I start with a question. Do I want to understand how the brain performs algorithm A or algorithm B? And then I decide on the game which has the elements that can separate these two. And once I do that, I recruit participants to play the game while their brain is being scanned. Now that helps me record the people's choices in conjunction with their brain activity. So now when I see that a person A is making choices that are more in line with algorithm A, I also have their brain activity and can see which regions are facilitating this process. And now this helps me build a functional map of decision-making circuit that is employing algorithm A. Now, why is this useful? This kind of knowledge can have far-reaching implications because once we underpin the decision-making circuits in the brain, we can also see what happens when the decision-making circuits goes wrong, or say in people with autism, schizophrenia, and people with other elements of neurodiversity. Now, this can help us build targeted therapeutic interventions like drugs that specifically target a region in the brain. And so my research not only helps us understand the origins of our intelligence, but it can also potentially help improve lives and thus enable us to embrace and cherish the diversity that has brought us so far down the evolutionary timeline. Thank you.
Thank you, Sneha Angu. Sneha is a second-year graduate student in the Social and Decision Neuroscience program. Her research interests lay in studying reward-modulated learning and planning by humans in complex state and action spaces. She is also interested in studying capacity limitations in cognitive machinery and their manifestations in everyday decisions. Her thesis advisor is Professor John O'Doherty. Presenter number 2 is Miles Chan, Division EAS Aeronautics Lab of the McKeon's Lab, presenting Turbulence. Small scale, big impact. Miles.
All of you have been profoundly affected by the chaotic swirling motion of fluid flow known as turbulence. Turbulence redistributes heat in our atmosphere, making it possible for Earth to support life. If you've ever had a bumpy ride on an airplane, you are acutely aware of the mighty strength of the swirling motion of the fluid flow around you. But more subtly, the cost of the airline ticket which you bought to go on spring break vacation is principally due to the cost of the fuel required to overcome aerodynamic drag, half of which is due to the turbulence on a much smaller scale. The fine scale is very close to a surface. In my PhD work, I focus on modeling and analyzing the smallest scales of turbulence very close to a surface. This near-wall turbulence is very important because it sets the dynamic behavior of the larger structures farther away from the wall. This near-wall turbulence is very susceptible to the shape and texture of the surface underlying it. The near-wall turbulence has historically been very difficult to study because it is very difficult, impossible, to place large physical probes very close to the surface. It's not possible to capture those fluctuations. And it is a testament to human ingenuity that we have any physical insight at all, due to the extreme difficulty of actually capturing any sort of data in experiments. By looking at the governing equations and incomplete data from experiments, we have been able to form some ideas of what's going on. But ultimately, we have been fundamentally missing a complete picture of the flow. And this is why I am excited about my work. Because with advances in computational capability, we have the ability to form some fully resolved data sets. And by interrogating those data sets, I can identify trends, relationships between the flow response and the roughness, which we were not able to find before. And I can combine this with the physical insights from scientists of the past to form new models, to train new models which can extrapolate from the simpler flows that we study as engineers to the more complicated flows which engineers actually have to deal with on a day-to-day basis. Models which run in minutes rather than months fundamentally changes the game. It enables simulations to take a larger role in the design process of aerospace vehicles. And that enables more design innovation and enables more environmentally friendly designs. In addition, a greater fundamental understanding of the phenomena of turbulence opens the possibility of control and mitigation, which could reduce the greenhouse gas emissions of transportation by as much as 50%. Solving turbulence would make the world a better place, and that is why I do this. Thank you.
He's developing reduced order models of turbulent wall-bounded flows using resolvent analysis in the research group of Dr. Beverly McKeon. Miles earned a BS in mechanical engineering at Georgia Tech, where he also studied how wombats make cubic poop, and subsequently received an Ig Nobel Prize in physics. Nowadays, Miles is frequently observed working with his laptop or with pen and paper, and may also be sighted running or cycling in the nearby hills or playing with his quartet. Thanks, Miles. Presenter number 3 is Benjamin Chang, Division EAS Applied Physics Lab Marco Bernardi Research Group, presenting Simulating Quantum Materials.
By controlling natural phenomena, we create technologies that transform our world. For example, fire is the control of matter, electricity is the control of charges, and internet is the control of light. And at this moment of human history, we are seeking the control of quantum interactions. When charge, light, and matter interact at the quantum scale, they can form materials with exotic properties that solve the grand challenges of the 21st century. For example, photovoltaic quantum materials can be used in energy, superconducting quantum materials can be used in medicine, and topological quantum materials can be used in computing. The properties of these quantum materials are determined by the underlying quantum interactions, which are described by the diagrams developed by Caltech's famous professor, Richard Feynman, where each line represents a single quantum particle in the material, and each intersection of the lines represents an interaction event. There are infinitely many diagrams of quantum interactions happening anytime and anywhere inside the quantum materials. However, they occur at such a tiny scale that even the most sophisticated instruments can have a hard time detecting them, which limits our understanding and imagination of their application potentials. This is why I'm passionate about simulating quantum materials. To stand on the shoulders of Mr. Feynman, to provide first principles understanding to quantum effects, and to bridge the gap between nature and technologies. To simulate quantum materials, we first solve the Schrödinger equation for each quantum particle, and then we calculate the equation that describe each interaction diagrams. Finally, we sum up as many diagrams as we can to make accurate predictions to the quantum material properties. Since we are investigating real materials, there can be millions of particles and so millions of equations to solve. This is why we use supercomputers to run our calculations, where we leverage many CPU and GPU cores to accelerate our calculations. In the past 5 years at Caltech, I have focused my research on simulating the quantum interactions between electrons and phonons, which are the quantum particles of atomic vibrations. Since then, I have made predictions to the electrical, structural, dynamical, and spectral properties of various kinds of quantum materials. My research has provided insights to decades-old quantum materials problems, like charge transport in organic crystals and high-temperature superconductivity. And today, I'm still thinking about developing new computational tools to simulate the diagrams, to predict material properties, and to bring blueprints to the next generation technologies. With this said, I hope you're as excited as I am about simulating quantum materials and transforming our world. I am Benjamin Chang, and I thank you for listening. Thank you.
Thank you, Benjamin. Benjamin is a PhD candidate in applied physics at Caltech. He is originally from Taiwan, where he received his MS and BS from National Taiwan University and National Tsinghua University, respectively. Benjamin's research focuses on harnessing the power of supercomputers to simulate the quantum dynamics and particle interactions in real materials. Through his thesis work, he aims to gain first principles understandings of exotic material properties with the goal of discovering design rules for the next generation electronic devices and technologies. Very cool. Presenter number 4 is Niyati Desai. She's at the Division of EAS, Space Engineering. Lab is Dimitri Mawe, Exoplanet Technology Lab, presenting Meet the Goldilocks.
Meet the Goldilockses. The Goldilockses are an alien family looking for a new home. They're all packed up and ready to go. Now the only question is where to? The Goldilockses aren't looking for somewhere too hot or too cold. They want somewhere just right. Each night on their home world, the Goldilockses set their telescope up in their backyard to look for planets. But whenever they look directly at a star, they're blinded by its light. This is because stars are about 10 billion times brighter than the planets themselves. If the light from a planet was one single drop of water, the light from the star is enough drops of water to fill this entire room. Today, 98% of all the exoplanets that we know about, we've found by looking at the stars and noticing them wobble or dip in their brightness, not from looking at the planets directly. That's where I come in. I'm an exoplanet real estate agent specializing in just right planets. I've got a special telescope that lets me see planets that others cannot. My telescope instruments block the light from the star and allow me to directly image the planets. These images are the only way to determine the surface temperatures and atmospheres of the planets to see if they're too hot, too cold, or just right. I'm trying to help the Goldilockses to find a new home. And to give them the most options to choose from, I still need to perfect my telescope. For that, I need 2 things. The first is one of these rainbow screens that blocks the light from the star. The second is one of these bendy mirrors to help focus all the starlight perfectly on the screen, so only the planet light can get through. Thousands of small actuators behind my mirror poke it to change its shape for each different star that I look at. And finding these optimal shapes is something that I'm still working on. But eventually one day I want to be able to ask, mirror, mirror, not on the wall, which planet is the most habitable of them all? Okay, but back to the Goldilockses. So to characterize a planet's surface to see if it's too hot or too cold, I need to get an image in full color. I've been working on designing my screen so that it can block the light from the star and do so at several wavelengths. So far, I've managed to cover the red wavelengths, but I need to cover more of the spectrum. I've been trying interesting designs like the spiral staircase and pinwheel patterns. But that's not all. So let's talk about galactic real estate for a second. In case you forgot, the 3 most important rules of choosing a new home, they are location, location, and location. And that is my final challenge. You see, there are already several planets that we can see, but those are all much farther away from their stars. Just right planets, where the Goldilockses might actually want to live, are much closer into their stars. But those are the hardest to see. So my goal is to design my telescope so I can take full color pictures of planets for planets that are close by to bright stars. Much like the Goldilockses, I've been searching for the just right combination of screen design and bendy mirror shape. And once my instrument upgrades are complete, I might even be able to help one of you find a new home. Is anyone out there looking for a new planet to live on?
Thank you. Niyati Desai is a 4th-year PhD student at Caltech working with Dimitri Mawe in Exoplanet Technology Lab. She completed her master's at Caltech and has a bachelor's degree in aerospace engineering and in physics from MIT. She is originally from New York, where she learned her love for the stars and faraway worlds through Star Trek. which she is still a regular fan of. When not in the lab, she is often found at the soccer field or volleyball court and also takes an active role in outreach on Caltech's campus. Very cool. Presenter number 5 is Abdullah Farouk, Division BBE Biology Lab, co-advised by Matt Thompson and Mikhail Shapiro, presenting flipping immune switches in macrophages with ultrasound.
This is Emily Whitehead. 10 years ago, Emily received an experimental immunotherapy for the treatment of an aggressive and rare form of leukemia. Amazingly, 10 years later, she's still completely cancer-free. We're at a moment now where, thanks to immunotherapy, curative treatments for cancer are possible. Immunotherapy involves harnessing our own immune system and retargeting it to kill cancer cells. However, if Emily had been diagnosed with a solid tumor like pancreatic cancer or lung cancer, her prognosis might have looked significantly different. That's because in solid tumors, we have to deal with an immunosuppressive tumor microenvironment. As you can see in the bottom left corner, a cold tumor is one that excludes immune cells and in which an inflammatory anti-tumor response is very difficult to mount. On the other hand, a hot tumor is one in which immune cells are able to enter into the tumor and actually mount an inflammatory response. So in order to make immunotherapy more conducive to an actual therapeutic context, we want to be able to convert cold tumors into hot tumors. And to do that, we can take advantage of the natural language that immune cells use to communicate with each other, called cytokines. These are small soluble proteins that can either ramp up or damp down the immune system. However, pro-inflammatory cytokines can be extremely toxic when injected systemically into a patient and have actually caused fatalities in clinical trials. My work harnesses the spatial precision of focused ultrasound with genetic circuits that enable the harnessing of that focused ultrasound to induce a biological response. So using focused ultrasound has a high degree of spatial resolution, and we can target a 2 millimeter region. Additionally, with focused ultrasound, we can induce hyperthermia, which actually induces a local elevation in temperature. That elevation in temperature doesn't actually destroy the tumor, but it acts as a switch, just like in electronics, and it catalyzes a DNA inversion. After that DNA inversion, a pro-inflammatory cytokine, in my case called IL-12, is able to potently stimulate T cells. We're currently working on testing this in mice, and our goal is to be able to create a system in which we can inject engineered cells into a patient, and then the user, physician, will be able to selectively define where and when an immune response is going to be mounted. Our goal is to make sure that cases like Emily's can be realities for patients with cancer, no matter what their type is. Thank you.
And thank you. That was Abdullah Farouk. Abdullah is a 5th-year graduate student in biology, co-advised by Matt Thompson and Mikhail Shapiro. Presenter number 6 is Sophie Miller, Division CCE, Chemical Engineering Lab, David Terrell Lab, presenting Shedding Light on the Night, uncovering the molecular signature of sleep.
We spend a third of our lives asleep. If our prehistoric ancestors could have survived without sleep, evolution probably would have taken care of this massive inefficiency for us. Clearly, there's something biologically important about sleep, since every creature in the animal kingdom does it. But we don't have to look that far to know how critical sleep is, because, especially here at Caltech, we all know what happens when we don't get enough of it. Yet, even though we spend so much of our time in this bizarre state of unconsciousness, much of the why and how of sleep remain a mystery. The first scientists to begin to tackle these questions have been biologists, who study the genes in our DNA and the circuits in our brain that are involved in sleep. But the genes in our genome and our brain architecture don't change on a 24-hour cycle. What is constantly fluctuating and more directly influences the changes in behavior and brain activity we see during sleep is the molecular composition of our cells. And that's where I come in. As a chemical engineer, I can help paint a more complete and dynamic picture of sleep by zooming in further and helping us understand sleep at the molecular level. The molecules I'm most interested in studying are proteins. Proteins are the molecules in our cells that do things. They're the signaling molecules, enzymes, transporters, structural components, and antibodies. For my PhD, I investigate what proteins cells produce during the night and how that differs from the protein cells produce during the day. To do this, I use the model organism called zebrafish because, believe it or not, we actually have a lot in common with these creatures. Zebrafish have a lot of the same genes known to play a role in sleep in humans, like melatonin, serotonin, and hypocretin. And as early as 4 days old, the larvae start exhibiting patterns of sleep at night and wake during the day, just like us. But when I came to this project, there was no way of picking apart what was being produced when. While we could get a snapshot at a moment in time of all the proteins in the fish, there was no way of distinguishing between which proteins were made at night and which were made during the day. To do this, I use a cool new method from my lab. It works by using a tagged version of the building blocks that make up proteins, which I give to the fish during the time window I'm interested in studying. The fish then incorporate this tag into proteins as they're being made, and the tag then allows me to pull out the newly made proteins from the pool of pre-existing proteins. I can then identify these proteins using an instrument called the mass spectrometer, which allows me to detect exactly which proteins were present in each sample and their relative amounts. Using this technique, I've identified thousands of proteins synthesized during day and night. And this data set, which I've only just started to dig into, will allow us for the first time to identify which molecules are uniquely synthesized during sleep and which during wake. What excites me most, though, about this data set are the questions that arise from it. Which proteins, what is the function of the proteins made at night, and how does that differ from those made during the day? And do proteins made at night directly facilitate sleep, or do they require sleep to be produced? I hope to answer some of these questions, and in doing so, shed some light on the sleep we get at night. Thank you.
Thank you, Sophie Miller. Sophie is in her final year of the graduate program in chemical engineering at Caltech. She works in Professor David Terrell's lab in close collaboration with Professor David Prober's and Professor Henry Lester's lab on developing and using chemical tools to better understand biology, specifically our brains at the molecular level. When she's not in the lab counting zebrafish larvae on her computer analyzing data of thousands of proteins, or trying to get the 8 hours of sleep per night her research has taught her are so important, Sophie packs the rest of her waking hours with rowing, volunteer coaching Caltech's women's water polo team, playing the baritone saxophone, cooking, and exploring LA's food scene. Sophie is passionate about teaching and mentorship and hopes to be a professor one day. Presenter number 7 is Marcos Nazareth Gallo, Division HSS Social and Decision Neuroscience Lab, Colin Kammerer Group, presenting A Warm Name Will Get You Hired.
So that's my full name, 28 characters. Yeah, it's very Latin. We'd like our names to be long, and it was kind of funny when I lived in China where people usually have names with 3 characters, and the professors would look at this and get shocked, and I would just be like, present, because I knew it was me. But what about when your name isn't just long or hard to pronounce, but actually carry negative stereotypes for those in the majority? What if I told you that every day in North America, thousands of people go without the chance of getting even an interview just because of their name, regardless of their resume? In my research, I ask, what role does name-based discrimination play in job applications from minoritized groups? So I gathered data from dozens of studies that send resumes to employers, which, unbeknownst to them, these resumes are actually fabricated to test their discrimination. And these resumes are identical with one key difference. Some of them carry a name that is stereotypical of a minoritized group, and others, the name from the majority group. And it's no surprise, especially to those from minoritized groups, that the Lakeishas and Tyrones and Alejandros actually get fewer callback invitations. What is striking is that I'm actually able to predict the likelihood of somebody getting a callback by asking independent raters one question: how warm and how competent does this name seem to the average American? Warm meaning good-natured and friendly. Competent meaning capable and efficient. And for every bump in warmth, the chances of somebody getting hired or somebody getting a callback increase. So if Tyrone was seen just as warm as Greg, the Tyrones would receive 33% higher chances of being interviewed. And people in minoritized groups know about this. They've learned to whiten their names, whiten their speech. Some really feel the threat of conforming to these stereotypes, creating undue stress and burden. So we must do something. Awareness is a good start, but hiring practices should be more transparent, and perhaps group information should be removed from initial stages of hiring. Effectively, intergroup contact and experience should reduce and change stereotypes, so that whether your name is 28 or 3 characters, we have the same chance of achieving our goals.
And thank you. That was Marcos Gallo. Marcos uses neuropsychological principles to inform and create effective public policy, including discrimination, education, and decision-making under poverty. His experiences growing up in a disadvantaged neighborhood in Brazil motivate him. He was a BA, he has a BA in economics and international development from Brigham Young University and an MSc in experimental economics from Shanghai Jiao Tong University. He is now a PhD candidate in social and decision neuroscience in the Kammerer Group. Thank you. Presenter number 8 is Jimmy Reagan, Division EAS, Space Engineering Lab Sunzhou Chong, Autonomous Robotics and Control Lab, presenting Making Spacecraft Drive Defensively.
If there's one thing I've learned since moving to Southern California, it's that it's important to keep an eye out for bad drivers. I was taught to drive defensively, that I can't assume others will be careful, and that my safety was my own responsibility. Why can't this be the same for our robots? In the not-so-distant future, swarms of spacecraft will work together to construct space stations, survey asteroids, or study the stars. But we can't make things foolproof here on the ground, let alone up in space. The more vehicles we have, the more likely it is that one of them will fail. And the closer together they are, the worse that failure might be. So, our spacecraft can't assume their neighbors will not fail. We need them to be responsible for their own safety. That's where my research comes in. I'm teaching spacecraft to drive defensively, and I'm doing so by giving them the tools they need to anticipate and better respond when things go wrong. On the road, when interacting with other drivers, we make predictions and assumptions about how people will behave. Spacecraft can do something like this too. Using knowledge of the spacecraft's hardware and what the swarm is trying to achieve, we can predict how each spacecraft's neighbor should act when everything is working versus how they might act when things are broken. For example, let's imagine we're trying to join a lineup of spacecraft. Our neighbor should slow down and merge behind us, but if their thrusters are broken, they might be unable to do so. We can start to anticipate these future dangers by thinking several steps into the future. But just like in a game of chess, these future interactions get very complicated very quickly. To handle this, I like to think of the future as a tree of possible outcomes, branching every time our spacecraft or their neighbors make a decision. These trees can get very big, but thankfully, we don't need to consider every possible future, just the ones where we might be in danger or where we might learn something about what is wrong and how we should react. By focusing on the most important possibilities, we can plan far enough into the future to act now in a way that gives us the best chance of staying safe, such as realizing our neighbor is on a collision course and that we should slow down and make some space, even if we technically had the right of way. In my work so far, I've taken this idea and developed the mathematical model or framework to translate this into a form that computers understand. And in doing so, I've made the process fast enough and accurate enough to run on real systems. For the rest of my thesis, I'll be working with JPL to apply this approach to upcoming missions. Just like learning to drive gives teens independence, and learning to drive safely gives their parents peace of mind. Enabling spacecraft to act independently will allow for more ambitious and complex missions than are possible today. And giving the spacecraft the ability to anticipate and react to unforeseen failures will make doing so safe enough to be a reality. Thank you.
Thank you, Jimmy Reagan. Jimmy is a PhD candidate in the Autonomous Robotics and Controls Lab, working with Professor Soon-Jo Chung. Jimmy's research activities include developing algorithms that enable spacecraft to perform autonomous fault detection, including in multi-agent or safety-critical settings using tools such as Monte Carlo tree search. Presenter number 9 is Nicholas Reed, Division PMA Physics Lab, Jim Fuller Taper Group, presenting Astro Seismology, the science of starquakes.
Picture a bell at the top of a faraway bell tower. Now, just by looking at the bell, you can learn certain things about it already, like its shape or its color. And that might tell you certain things, like what it's made of. And heck, if you were clever and you even knew how far away the bell was, you might even be able to figure out its size. And all that's cool, it really is. But now, suppose you could listen to the bell ring. Now, that would tell you something different because, well, a hollow bell sounds different than a solid bell, sounds different than a bell filled with cheese or whatever. And so suddenly, by listening to the rings of the bell, you learn information not just about the bell's surface, but also its deep interior, which was something which was before just totally invisible. The idea of astroseismology is pretty much exactly like that, but instead of listening to bells, we're listening to stars. One of my favorite kinds of stars to listen to is the red giant, a puffy dying star with a dense helium core at its center. Red giants have unending starquakes owing to constant stirring and ringing by convection in their outer layers. And by monitoring the changes in brightnesses of these stars, we can listen in on those starquakes, peer underneath the surfaces of these stars, and measure the masses of those helium cores. I'm going to oversimplify a little bit, but essentially, more massive stars will make and have more massive cores. Now that kind of makes sense. And so indeed, when we go and look at them, red giants tend to have the cores with about the masses that we expect. But every once in a while, you stumble upon a red giant whose core is just a little bit too light. It'd be like wandering into a bell factory and finding a single solid bell in a pile of hollow ones. Now, you might not know why this bell is different, but you know that it is, and that it was probably made differently somehow. And in the case of stars, well, an undermassive core rather suggests that the star was less massive when it made that core than it is now today. That means it had to pick up that mass somehow. And so we've discovered, using astroseismology by listening, a way to tell, even potentially millions of years after the fact, that a star participated in a violent stellar merger event. That is only one of the many problems about which astroseismology has something to say. You know, we astronomers, we care so much about looking. We build these gigantic telescopes for billions and billions of dollars. We even shoot them into space just so we can look at stuff harder. But astroseismology teaches us that there is a heck of a lot more we can learn about the stars by listening. Thank you.
Thank you, Nicholas Reed. Nicholas joined Caltech as a graduate student in the fall of 2020 and has studied stellar oscillations and interactions ever since. He graduated from UC Berkeley in the spring of 2020 when he was interested in stellar dynamics and diamond defects. In his free time, he likes to sing, dance, run, play chess, and practice martial arts. Presenter 10 is Adam Shaw, Division PMA Physics Lab, Manuel Endres Lab, presenting Building a Hidden Universe, one atom at a time.
The world around us can often seem random, whether it's coin flips or airplane turbulence, lightning strikes. And so much of the work of science for so long has been to try and peer past this layer of randomness, trying to understand why nature behaves the way it does underneath. But my interest is in why there's a barrier of randomness at all. How does randomness and chaos emerge from the simplest of systems? To tackle this problem, I try to look to the smallest scales possible, one atom at a time. In my research, I use a combination of vacuums, lasers, and magnetic fields to create an environment which is almost completely decoupled from the outside world. And into that environment, I inject just 100 single atoms. I can move those atoms around programmatically as if they were little atomic Lego bricks, and I can use them to form complex structures like the Caltech logo, spelled with only 80 atoms. And these atoms really form their own little universe where we can completely turn off the noise of the outside world And the question I want to ask is essentially, is randomness intrinsic even to this most pristine of systems, or is it just some artifact of interactions with the outside? So to study this, I play a game of atomic telephone. I set the atoms up in a chain, and then I shine ultraviolet light on them. That makes the atoms get excited, makes them start talking to each other. And they start with their nearest neighbors and send information down the chain. And then I look at the end of the game and I see how information has developed, and I see a complex structure emerge where all the atoms form one collective state. But something changes if now the interaction with the environment starts changing over time. For instance, if the power of the ultraviolet laser starts fluctuating. In that case, that complex order breaks, and the message that we want to read out from the atoms at the end of the game, it becomes garbled and unrecoverable. Essentially, what my research so far has shown is that even the most pristine systems have a tendency towards highly fragile states, which are highly susceptible to small perturbations, causing chaotic outcomes. But with our 100 atoms, we're able to study this process and turn up and down the noise so that we can understand the same transition from order to chaos in our outside world. And now that we understand how randomness can emerge, and how it can corrupt our game of telephone, we're able to build around it. And so we can construct our atoms into different types of structures that are impervious to different types of noise sources. And by doing that, we're able to study a whole host of science, ranging from fundamental physics to materials chemistry or applied chromatography. And so we're really trying to enter a new paradigm in how we interact with the world around us. We're no longer just constrained to observe nature. Instead, using our type of atomic telephone, we can build nature ourselves, one atom at a time. Thank you.
Thank you. That was Adam Shaw. Adam is a fifth-year physics graduate student in the lab of Manuel Andres. His research focuses on using ensembles of individually controlled single atoms as the building blocks for finding useful applications of quantum mechanics, for studying aspects of fundamental physics, and generally for doing science impossible to reach on any classical computer. Presenter number 11 is Skylar Ware, Division CCE Lab Kim C's group, presenting WaterFree Electrolytes for a Sustainable Future.
How would you like to charge your phone only once a week? Would you be more willing to buy an electric car if it could take you twice as far as it does now? How might your world be different if you could pay less for medicine? Believe it or not, all of those scenarios are in our reach. But to achieve them, we need to use electricity to power new chemical reactions. Most reactions that are driven by electricity happen in solutions of electrolytes. It's not quite the same as Gatorade, but it works in much the same way. Electrolytes are charged particles that help electricity move through a system. When we drink Gatorade, the electrolytes we consume help power our muscles. And when we do chemistry with electricity, the electrolyte solutions help power a device or a reaction. For many reactions that use electricity, like capturing energy with solar cells, we use water-based electrolytes. Most of the time, those work just fine. They're cheap, they're safe, and they're easy to make. But there's a problem. Just like how water will evaporate at high enough temperatures, it will also break down into hydrogen and oxygen under a strong enough electric current. That means we can't put Gatorade in our batteries, and we can't make medicines with Pedialyte. We'd end up breaking down water instead of making the products we want. So what can we use instead? Well, that's where my work comes in. As an electrochemist, I develop new electrolyte solutions that don't contain any water. Instead, I dissolve the electrolytes in a different liquid that's far less likely to break down, often the same types of liquids used in perfumes and cleaners. These water-free electrolytes allow us to do new chemical reactions with electricity. Perhaps the most tangible application of water-free electrolytes is in batteries. I've worked with a team to design new electrolyte solutions that could help us power research vehicles on other planets. But we draw on the same principles to power electric cars, trucks, and airplanes here on Earth. We could even use them to one day power our cities with renewable energy. And it's not just batteries. Using electricity can drastically reduce the amount of specialized and expensive chemicals that we need to make medicines. Our team has developed water-free electrolytes to recycle one such chemical, samarium iodide, which is used to make cancer treatment drugs and antibacterial products. With our new electrolytes, we hope to use 90% less samarium iodide to make the same amount of medicine. WaterFree Electrolytes will help us build a world where we can take a cross-country road trip in an electric car, where we never get stuck begging to borrow our friend's phone charger, where our lifestyles are more sustainable, and perhaps most importantly, where life-saving medicines are more affordable and accessible for all of us. Thank you.
Thank you. That was Skylar Ware. Skylar is a fifth-year graduate student in the Division of Chemistry and Chemical Engineering, advised by Professor Kim See. Her thesis research focuses on developing new electrolytes for next-generation batteries and electrocatalysis. She is originally from Ohio and earned her bachelor's degree in chemistry from The Ohio State University in 2018. Outside of labs, she enjoys hiking, reading, acting, and playing tabletop RPGs. Presenter number 12, Nitika Yadlapalli, Division PMA Astrophysics, Lab Vikram Ravi Radio Astronomy Group, presenting astronomical forensics using millimeter waves to investigate stellar death.
Picture this. You're a detective and you get called to the scene of a crime. When you get there, you learn that someone has died, and now it's become your job to figure out what happened in the events leading up to their death. Where would you start? As an astronomer, I act like a detective in the same way. The most massive stars in our universe, stars many times bigger than our own sun, will call us to the scene of the crime by dying in these powerfully bright explosions known as supernovae. Now, before these spectacular explosions occur, the original stars are far too dim for us to see. However, the mystery we want to uncover is how are these massive stars evolving in their late stages? And to chip away at this puzzle, we need to use some forensics of our own. Let's start by asking a question. Where are these stars when they're exploding? The environment surrounding stars hold precious information about their final days. Massive stars are enshrouded in these hydrogen envelopes, and in the final months and days of their lives, these envelopes will get expelled out into the space surrounding the star. Then, the supernova explosion that follows will generate a powerful shock wave that moves through and interacts with this material. This interaction is what produces millimeter waves, a key clue to cracking our case. The brightness of the millimeter waves can tell us about how much material was expelled. The pattern of the millimeter waves can tell us how was it expelled. Was it slow and continuous, or was it in many big bursts? And finally, a key element is that these millimeter waves are brightest when our supernova shock is smaller and faster, and the material it's moving through is denser, meaning it's brightest very soon after the supernova explosion occurs. And this is very important to us, because the sooner we detect any emission from the supernova, the closer in to the time of death of the star we're actually investigating. So answering questions like these is why the focus of my thesis project has been to commission a new millimeter telescope called SPRITE. Located just a few short hours north of Caltech, SPRITE is one of the few millimeter telescopes in the world, and we have the unique power of controlling its entire observing program. By creating this resource that is dedicated to observing supernovae and similar phenomenon, we have the ability to frequently and promptly revisit these cosmic crime scenes and build up a detailed record about how the millimeter brightness of these crime scenes are changing with time. With this abundance of new information I plan to collect using SPRITE, we stand to push forward our understanding of how life and death works in the cosmos. Thank you.
And thank you. That was Nitika Yadlapalli. Nitika is currently a fifth-year graduate student in astronomy, working with Vikram Ravi in the radio astronomy group. Her research is primarily on millimeter waves from the high-energy universe, with a focus on instrumentation at the Owens Valley Radio Observatory. She is graduating in June and will be starting a postdoc at JPL in September with a NASA postdoctoral program fellowship. Finally, presenter 13, Dominic Yerk, Division EAS, Electrical Engineering, Lab Yasser Abu Mustafa, presenting what guitar strings can teach us about blood pressure.
Hi, I'm here to tell you what guitar strings can teach us about measuring blood pressure. Now, you might be wondering, When I go to the doctor, they already measure my blood pressure using an inflatable cuff that squeezes my arm, and that seems to work just fine. So why do we even need more research into this? The way I like to think about it is that taking blood pressure with a cuff is like taking someone's pulse at their wrist. The pulse is useful, but it only gives you one summary number, which is the heartbeat. To get more detailed information, doctors will hook you up to an EKG, which gives them not just a summary, but a full picture of how your heart is behaving. To a medical professional, every bump and wiggle in this graph can give them insight into medical problems like cardiac clots that would not be detectable from the pulse alone. Similarly, taking blood pressure with a cuff is definitely useful, but it only gives you a summary of the maximum and minimum pressure values. And in between these, there's a lot of valuable information about various health problems, like arterial valve failures, that can only be seen in the bumps and wiggles of this full continuous data. The problem is that currently, the only way to get this full blood pressure data is arterial catheterization, which is a difficult and invasive procedure that's only done in critical care settings. The goal of my research is to find a way to collect the same data, but to do it easily and non-invasively. So now we come back to my inspiration, which is the guitar string. When you strum a guitar string, it resonates at a specific frequency that's determined by how much tension it's under. And when you tune your guitar, you're changing this frequency by changing that tension. The key insight in my research is that arterial walls can vibrate just like a guitar string, and the same physics rules apply. This means that arteries will resonate at a specific frequency, which is determined by blood pressure, and as the blood pressure changes, this frequency will change with it. My device takes advantage of this relationship by strumming the artery using a small speaker pressed up against the skin, while an ultrasound wand simultaneously measures how the artery is responding to these strums. By making repeated measurements of the resonance frequency, I can calculate full continuous blood pressure graphs like the one shown up here. The device has already gone through initial human testing, and its performance is not that far off of the gold standard of the invasive catheter. My hope is that with further work to improve both the accuracy and miniaturization of this device, we'll be able to put devices like it in every doctor's office and provide much wider access to this important information about the health of our arteries. Thank you.
And thank you. That was Dominic York. Dominic began his scientific career as an undergraduate at Caltech, majoring in physics. Over time, his interest shifted from theoretical questions to more tangible applications, particularly those related to biology and medicine. After taking a break from academia to work at a biotech startup, Dominic returned to Caltech to pursue his PhD in electrical engineering. He continues to focus on methods of applying concepts from physics to solving biomedical challenges. Now, we're going to bring up Kara again. All right. All ready for this?
All right. That concludes our competitor presentations for this evening. Please join me in another round of applause for our graduate students. While our judges confer and tally their scores, I'd like to take a moment to thank our diamond sponsors for this event this evening. First, I'd like to tell you about EBSCO Library Services. EBSCO is a proud partner of Caltech Library, and they are very honored to support the 2023 3MT competition. EBSCO provides institutions with high-quality, essential content and resources for research from thousands of publishers to ensure success for students, faculty, and staff. You can find EBSCO resources using the Caltech Library at library.caltech.edu. Our second diamond sponsor this evening is Elsevier. As a global leader in information and analytics, Elsevier helps researchers and healthcare professionals advance science and improve health outcomes. You may be more familiar with Elsevier through their Science Direct platform for journals and ebooks, which you can also access at library.caltech.edu. And our third diamond sponsor this evening is Science of Synthesis Team of Chemistry, and they provide a critical review of the synthetic methodology developed from the early 1800s to date for the entire field of organic and organometallic chemistry. Science of Synthesis is a full-text resource for methods in synthetic organic chemistry. Thank you very much to our sponsors. All right. I'd like to give a special shout out to our communications coaches before I announce the winners. I'm not going to make you wait too much longer, I promise. But for all of our finalists, we offered the opportunity to meet with communications coaches, and I'd particularly like to thank Chris Daly, the library's communications coordinator, Paul Propster, the story architect and senior strategist at NASA and JPL, Suzanne Hall, the director of the Hickson Writing Center, Aaron Burkett, the science writing specialist at the Hickson Writing Center, and Robin Javier, STEM communications specialist and lecturer in the Division of Engineering and Applied Sciences. And for any of you Caltechers in the audience who want to improve your science communication skills, the Hickson Writing Center is a really great resource for our community, and you can find out more about their services and book appointments at writing.caltech.edu. And I'd like to give a plug to the Storytelling for Scientists class that our very own Brian Brophy, where did you go, Brian Brophy, teaches every term. Brian also offers appointments for science storytelling coaching. So any of us who want to get better at telling our science through stories, Brian is there for us. So without any further ado, I have the pleasure of announcing our winners. So I'm going to do them third place to first place. So starting in third place, our winner is Dominic Yerk. All right, in second place, Skylar Ware. All right, first place winner, and the winner of a $3,000 prize, Niyati Desai. Thank you to all of tonight's participants, to our esteemed judges, and to our generous sponsors. And thanks to all of you for bearing with us with our hiccups this evening. Thank you for attending this event. We look forward to seeing you all in person or via live stream at next year's Caltech 3MT competition. For those of you who are joining us in person tonight, we have some light refreshments in the Cahill Library, and we invite you to join us for those. And while you're out there, if you see somebody wearing a 3MT staff tag, that's one of your Caltech library workers. Today is National Library Worker Day as part of National Library Week, so join me in thanking them for the work that they do for all of us all year round. Good night, everyone.